Welcome everyone. Today we'll be restarting the Lattice seminar, but over Zoom this time. And the first talk now will be given by Tamer. He will talk about the recent development of NIZK.
Perfect. Thanks for organizing this. Cool. So yes, I'm going to talk about a new work where we. I'm hearing lots of background noise, so cool. So yeah, like I said, we construct a new NIZK protocol based on the LPN assumption and assuming the existence of Trapdoor hash. Maybe one of the more exciting bottom lines of this work or implications is the first NIZK from LPN and DDH, which are both standard assumptions that were not known to imply NIZK before. So this is the joint work with Fika and Denkata. And let's start. So let me just define NIZKs real quick. So what is NIZK? It's non-interactive zero-knowledge protocol. So it's basically a proof system where we have a prover and a verifier and some statement that an input X is in some NP language L. And we're going to assume that the prover is efficient given an NP witness for the statement. We're going to be working in a model where both parties have an access to a common reference string, a CRS, which we assume is generated in a trusted setup before the invocation of the protocol. We require that the protocol is non-interactive, and therefore it consists only of a single message. So the prover is going to just send a proof pi, and the verifier is going to either accept or reject. And we require the standard completeness, soundness, and zero knowledge requirement. So completeness basically says that if the statement is true, then the verifier accepts. If soundness means that if the statement is false, then even a cheating prover cannot convince the verifier that it's true. And zero knowledge says that a verifier cannot learn any extra information given the proof other than the validity of the statement. This is pretty standard, everything here. There are many applications of NIZKs, and they are interesting objects by themselves. I'm not going to spend a lot more time on discussing the applications. Perfect. Question? Okay. So before I start talking about what we do, let's kind of survey the approaches that are known to construct NIZKs, understand the assumptions. So maybe the textbook approach to do that is called the hidden bits model. And the only known way to instantiate this model is using trapdoor permutations. And as far as we know, we can construct trapdoor permutations only under factoring related assumptions. So this approach is still limited in this sense. A more recent line of work construct NIZKs using groups with bilinear maps. So we make Diffie-Hellman style assumptions on these groups, and the constructions themselves are very non-generic. They heavily rely on bilinear maps in these groups. Cool. So I don't think there's okay. Let's just proceed. So there are these two approaches which are kind of limited in terms of what set of assumptions we can base their security on. And lastly, there's this approach of using Fiat-Shamir transform in order to take a zero knowledge protocol and turn it into a non-interactive zero knowledge. I mean, many works have tried to construct NIZKs using this approach in a provably sound manner, and this line of work eventually led to constructions that are secure under standard lattice assumptions. This is pretty new from last year. Good. So our work is can be kind of put under this in this framework of constructing NIZKs using Fiat-Shamir. And in order to instantiate Fiat-Shamir in a probably sound manner, we go through a notion called correlation tractable hash. Superior work could construct a relation tractable hash under LWE. In our work, we show construction of a NIZK protocol under the LPN assumption, like I said, and using Trapdoor hash, which by itself can be instantiated under DDH in particular. Good. Are there any questions so far? Perfect. Okay. Let's start discussing this approach of constructing NIZKs using correlation intractability. We start with a zero knowledge protocol that consists of 3 messages, and we assume it's public coin, meaning that the very first challenge in the second message is just a random, consists of just random coins. And the Fiat applying the Fiat-Shamir transforms over this protocol means taking some hash function h and letting the prover emulate the original 3-message protocol by himself. So the first message is just computed as before. So let's say the first message is A. So the prover computes A and sends it to the verifier. And now in order to compute the verifier's challenge, the prover computes the hash value of A. So the verifier challenge in this non-interactive protocol is essentially the hash of A under a hash key, which is sampled randomly, and we consider it as a part of the CRS. So now that the prover has his first message A and the verifier's challenge, which is the hash of A, he can compute the third message and send all these 3 messages to the verifier B. And you can clearly see this protocol is non-interactive. And if we start with the public coin protocol, then you can easily see that this protocol is also complete. It is also not hard to show that if we start with an honest verifier zero knowledge protocol, then the Fiat-Shamir transform preserves zero knowledge. Okay, and there's no sense in talking about honest verifier here because the protocol is non-interactive. So we have completeness and zero knowledge, and all is left to argue is soundness. So if we start with the 3-message sound protocol, then it's not clear that the Fiat-Shamir transform preserves soundness for the reason that the prover has some control over the verifier's challenge. So the verifier's challenge is no longer sampled by the verifier, but is rather computed by the prover over the first message. So you can think about a cheating prover that would try to choose a first message whose hatch gives him a challenge that may let him cheat and convince the verifier that a statement is true, although it's not. So this leads us to focus on a very specific type of 3-message protocols that we call sigma protocols. In a sigma protocol, if we fix a CRS and an input X and a first message, a prover's first message A, then we ask that there exists only a single verifier's challenge that may possibly allow the prover to cheat. So again, I'm fixing a CRS, an X that is not in the language. So we have a false statement here and a first message. And we say that a protocol is a sigma protocol if it has a unique bad challenge, or in other words, if there exists only a single bad challenge, E, and by bad challenge, we mean a verified challenge that for which there exists a proof that accepts. Perfect. And given and based on the fact that there exists a single bad challenge or a unique bad challenge, we can define a function that is defined by the ACRS and the input X and takes as input a first message and outputs the bad challenge E. So I'm going to refer to this function as the bad challenge function from now on. Good. So now we ask, when does the Fiat-Shamir transform preserve soundness in this case? So we can see that if we can claim that it's hard for the prover to find a first message A such that the hash of A, HA, is this bad challenge, then it will be hard for the prover to break the soundness of the protocol. because you will never be able to find a first message and where its hash, which is essentially this very first challenge, is the bad challenge. And we're going to call this notion or this security requirement correlation interactability. So we say that a hash function is correlation interactable for the bad challenge function if it's hard to find such an A. Any questions? Good. Okay. So now we have a recipe for constructing NIZK. So first of all, we need a Sigma protocol. And what else we need is a correlation interactable hash for the class of bad challenge functions. If we have these two, we can apply the Fiat-Shamir transform over the Sigma protocol using the correlation interactable hash and get a provably sound NIZK protocol. Perfect. So the guiding rule kind of this approach, or in order to instantiate this recipe, is to describe the bad challenge as simple as possible, or in other words, to make the complexity of the bad challenge complexity as low as possible, because the lower the complexity of the bad challenge, then intuitively the simpler the task of constructing correlation interactability for these kind of functions become. Okay, this is a pure intuition. Again, intuitively, constructing correlation interactability for simpler functions is simpler. So now start asking questions. First question we should ask is how simple this bad challenge can be. Again, we have to start with the Sigma protocol, the protocol that is zero knowledge and sound. So we cannot just take any protocol and apply Fiat-Shamir. So we ask how simple can a bad challenge function of a Sigma protocol be? And once we know more or less the answer to this question, we also have to ask what kind of correlation interactability we can obtain under standard assumptions. So against what functions we can protect in correlation interactable hash under standard assumptions. Good. So the first work that tried to instantiate this paradigm in a provably sound manner is this work by Kaneta et al. That dates back to 2016. And there they observe that the bad challenge function is efficiently recognizable. So they say, if I give you a bad challenge, then you can efficiently recognize it's a bad challenge. And therefore, the goal of constructing NIZK reduces to the goal of constructing correlation interactability for such functions. And then they show how to construct correlation interactable hash for functions that are efficiently or relations that are efficiently recognizable, and they do that based on pretty wild assumptions. So they assume sub-exponential indistinguishability obfuscation and some other strong notion of obfuscation. This line of works continues with many interesting works, and again, each of these works propose the construction of correlation interactable hash for some class of functions that captures the bad challenge function in some Sigma protocol. But again, all of these protocols, they assume assumptions that are far from being standards. Standard, in particular, they either assume obfuscation or KDM with optimal security. Very recently, in fact, last year, we finally, this line of work finally led to constructions under standard assumptions. And so it started with this work of Kaneta et al., where they rely on the observation that the bad challenge can be actually efficiently computable in some Sigma protocols. And now the goal becomes to construct correlation interactability for efficiently computable functions. And they show how to do that using circular secure full homomorphic encryption, which can be instantiated under circular secure LWE. And then Pikert and Shehan show how to do that based only under plain LWE. Okay, so this is the first work that instantiates the Fiat-Shamir for NIZKs based on standard assumptions. Good. So in order to try and construct NIZKs under other standard assumptions, we observe that all these works, they consider the complexity of computing the bad challenge. Okay, so now I'm focusing on these last two works. So they focus on the complexity of computing the bad challenge. And because the bad challenge can be a general polytime computation, then it seems that the techniques that we need to construct relation intractability have to go through some fully homomorphic constructions. So, for example, here we use a fully homomorphic encryption. This work essentially relies on some form of homomorphic commitments, all based on LWE. So we kind of diverge from this line of work and consider the complexity of approximating bad challenge. So usually when there's something that's hard to compute, you try to approximate, right? So now we focus on the approximation complexity of bad challenge, which is hopefully much simpler than the complexity of computing bad challenge. And we hope that by focusing on the approximation complexity, then maybe we can make the correlation intractability task much easier. And we actually show that it is possible. And so in particular, we show that based on the LPN assumption, there are some sigma protocols where the bad challenge function can be approximated using constant degree polynomials. And having this, we can now construct relation intractability for functions that are approximated by constant degree polynomials and obtain NIZKs. And it appears that constructing such correlation intractable hash can be done using Trapdoor hash, which can be based under DDH, QR, DCR, or LWA. I see someone raised the hand.
So I don't, can you define what approximating the bad challenge means?
Sure, definitely. I'm just providing a high-level overview here. I'm gonna go through all the details much later. But again, I just want to give you the intuition of why we did is useful in general. So again, instead of considering the bad challenge or its complexity, its exact complexity, we consider its approximation complexity, and this allows us to reduce the task of constructing correlation intractability from constructing correlation intractability for all efficiently computable functions to constructing correlation intractability for functions that can be simply approximated by constant degree polynomials. And constant degree polynomials are very, very simple objects. I hope I answered partially your question.
Let me see if I understand. So it's not that the function that you're trying to build correlation intractability against is still like the same function. It's the bad challenge function. You're just using, instead of like looking at like a sort of more natural complexity notion, like it should be efficiently computable or something like this, you're using this approximable by constant degree polynomial.
So we actually take a special instantiation of this sigma protocol under LPN. Okay, so I'm going to talk about it, but in a high level, sigma protocol uses some commitment scheme. And we show that if this commitment scheme is some commitment scheme which is based on LPN, then this bad challenge function, which contains some operations related to this commitment scheme, can be approximated by constant degree polynomial. Okay, so this is not true for every bad challenge function of any sigma protocol. Any other questions? Okay. Cool, let's proceed. So before talking about how to approximate bad challenge and how to construct correlation intractability, let me just convince you that bad challenge can be even efficiently computable for some useful sigma protocols. Okay, this is not clear. Good. So my goal now is to show you a sigma protocol where the efficient bad challenge is computable efficiently. And now let's keep this outline in mind. So our ultimate goal is constructing NIZK for MP, and we show, at least not formally, but I explained to you why this goal reduces to the goal of constructing correlation tactable hash for the bad challenge function of some sigma protocol. Perfect. Okay, so maybe the first example that comes to mind when we talk about zero knowledge, or at least one of the first examples, is the zero knowledge protocol for graph Hamiltonicity. So the statement is that some graph G has a Hamiltonian cycle H. Okay, and this is an NP-complete language, of course. So we have a graph G and the Hamiltonian cycle in H, and the prover wants to prove to the verifier that such a Hamiltonian cycle exists in G. So the first thing that the prover do, he chooses a random permutation pi and applies it over H. So now we have this random permutation of H, and I remind you, H is just a cycle, so this is just a random cycle graph. And now the prover commits on this graph. And next, the verifier samples a random coin, which is a public coin, and sends it to the prover. And now there are two cases. So if the challenge is 0, if E is equal to 0, then the prover decommits to the entire thing. He reveals the permutation on H by H, and this clearly reveals nothing, right? Because this is just a random cycle. On the other case, when E is equal to 1, then the prover decommits to a subset of the commitments he sent in the first message. And more specifically, he decommits to the edges that correspond to non-edges of G. So the important thing to remember is that in the third message, the prover decommits to something that was committed on in the first message. And now once the decommitments are received by the verifier first checks that the decommitments are valid. And if E is equal to 0, then he verifies that the graph is indeed a cycle. And otherwise, if E is equal to 1, he checks that what he received are decommitments to non-edges of pi of H as well. So I'm not going to go into the details, but whoever has seen this, then he's probably already convinced that this is complete, sound, and zero knowledge. For those of you who didn't see this before, then you're gonna believe me that it's really easy to show that these requirements hold. So I'm taking this protocol as an example for a more general abstraction that we call a commit and open sigma protocol. So I'm going to look at protocols where the prover first generates some proof pi and then commits to this proof. So the first message of the prover is just a commitment to some proof. And along with the proof pi, the prover prepares two subsets, pi 0 and pi 1. So these are two substrings of pi. And now the verifier sends his public challenge, and once the challenge is received, the prover decommits to the substring corresponding to this challenge. So if the challenge is 0, he decommits to pi 0, and otherwise he decommits to pi 1. And in commit and open sigma protocols, the verification consists of two verification machines, V0 and V1. And the verification simply consists of first verifying that the decommitments are valid. So first the verifier verifies that the openings are okay, that they are not illegitimate. And the next thing he runs the corresponding verification algorithm. So he takes VE and computes it and runs it over pi E. Okay, so again, we can kind of split the verification into two parts, each corresponding to one case, depending on the value of the challenge. So why am I bothering to take commit and open sigma protocols? And the reason is that I can kind of describe the bad challenge function in such protocols very easily. So let's see. So what happens when the unique bad challenge is equal to 0? Then by the definition of the unique bad challenge, a cheating prover cannot cheat when the challenge is 1, right? Because the bad challenge is unique. And therefore, the verification in the one case must fail. So we know that V1 on pi1 is equal to 0. On the other hand, when the unique bad challenge is 1, then we know that a cheating prover can cheat in the one case, and therefore V1 on pi1 is equal to 1. And now you can see that the unique bad challenge can be simply computed by running V1 on pi1. Okay, so the bad challenge corresponding to the CRS-X and the first message A is V1 invoked on pi1, where pi1 is are the values that are underlying the commitments in A. Perfect. So it's not clear that in general this function is computable. It's not clear how to extract pi1 out of A, but we know that when the commitment scheme is extractable, meaning when we can extract the committed values out of the commitment using some trapdoor, then this function is computable. So we simply extract pi1 using the extraction algorithm of the underlying the commitment scheme, and then we run v1, which is just some polytime computation. Perfect. So now we know that when we use a commitment scheme, an extractable commitment scheme underlying this commit and the Open Sigma protocol, then the bad challenge of this protocol is efficiently computable. And this means that if we have correlation intractability for all computable functions, then we get NIZK. How? By simply applying the Fiat-Shamir transform using this hash function over commit and Open Sigma protocols with an extractable commitment scheme. And this is essentially what these two works do. They construct correlation intractability for all efficiently computable functions under, in particular, under LWE. Any questions? Good. So now that we talked a lot about Fiat-Shamir and correlation intractability, we haven't really defined what correlation intractability is. So we say that a hash function is correlation intractable for some function f if no adversary can find a correlation between h and f. More concretely, let's define this security game, which we call the correlation intractability game. So in this game, we sample a random hash key, k, and then we ask the adversary to give us some input x, and the adversary wins if and only if x is a correlation between h and f, meaning that h of x under this hash key is equal to f of x. So if this game is hard to win, then we say that h is correlation intractable for f. And we say that h is correlation intractable for a function class f if it is correlation intractable for every function in the class. Any questions regarding this? This is important and a bit, this notion is a bit different than anything at least I saw in crypto, so cool. Okay, so to get a better sense about correlation intractability, let's first try and see if it's an easy task sometimes or not, if it can be trivial at all. So what happens when we try to construct correlation intractability for a single function, or when our function class contains a single function f? Any ideas? Can we easily construct correlation intractability in this case against f? Okay. So it appears that constructing CI for a single function is actually easy. You can just define your hash function to be fx plus 1. And it's clear that hx is never equal to f of x. Notice that I didn't even use the hash key. And this idea is actually easy to generalize when your function class contains only polynomially many functions. So if your function class is small, then it's easy to construct correlation intractability. correlation intractable hash. Sorry. Okay, so what happens when your function class f contains only length expanding functions? So now your class may contain exponentially many functions, but I tell you that all functions in the class are length expanding. What happens now? So it appears that also in this case, it's easy to construct correlation intractable hash. And the construction I'm suggesting is the following. So let the hash key be just a random string r, and define the hash function to just output r regardless of the input. So the hash function is a constant. So we define hx to be just r, and this is a random string that is determined by the hash key. And now notice that if the function is sufficiently expanding, then we can claim that with negligible probability r is even in the image of f, sorry, and therefore there exists no x with overwhelming probability such that h of x is equal to r. Are these two examples clear? Good. If I'm not getting any questions, then I assume they are clear. But please do ask if they're not. So now we know that correlation intractability is a non-trivial task when our function class is sufficiently rich, if it contains sufficiently many functions, and it contains arbitrarily compressing functions. So the case when our functions are expanding is not interesting. And unfortunately or interestingly, the class of bad range functions is such a class. So it contains many functions, and they are compressing. So NIZKs are non-trivial. If anyone doubted, they are. Good. Okay, so I'm going to discuss an approach towards constructing a correlation intractable hash that was introduced in prior work. So we say the following: if we want to construct a correlation intractable hash H, then it's sufficient to construct a hash such that for every f in the class, we have a distribution over hash keys, which is a fake distribution. So for every function, there is some fake distribution over hash keys that is indistinguishable from the real distribution over hash keys. So we can sample a key given some f that looks indistinguishable from the hash key. And what we require from this fake hash key is the following. So we require that the correlation intractability game, when we sample a random fake hash key rather than a random real hash key, so we require that this game is statistically hard to win. Again, this game is identical to the correlation intractability game. Except that we sample a fake hash key. So again, we're sampling a fake hash key, and then the adversary's goal, given this fake hash key, is to find a correlation. So his goal is to find an x such that h with the fake hash key is equal to f of x. And it's not hard to see that if these two conditions hold, then h is correlation intractable for all functions in the class. And this is simply because if the adversary is able to break the correlation intractability game, the real correlation intractability game for some f, then he must have distinguished between the fake hash key and the real key, because the correlation intractability with the fake hash key is impossible to win, even for an unbounded adversary. And a different way to look at it, which may be easier, we can switch the correlation intractable game to the fake correlation intractable game for some f based on this indistinguishability between the fake hash key and the real hash key. And now we can claim that correlation intractability is hard because this game is statistically hard to win. So now our goal becomes the following. We aim at constructing a hash family H such that for every function in the class, we first of all have a distribution over fake hash keys, which we denote by K sub f. And we want that the correlation interactability game with K sub f is statistically hard to win. And in other words, we require that there exists no correlation between H K sub f and f, except for negligible probability. So we want the probability that there exists at all some x for which h of x is equal to f of x with this fake hash key is negligible. Any questions? Yes.
Yeah, so actually I don't understand the difference between this fake hash key and the real key. So what is really, is there some difference in the function of the definition of the hash function, or I don't get?
Yes, so it's simply a different distribution over hash keys. So notice that it's impossible using some statistical arguments. You can show that it's impossible to get statistical correlation interactability for all functions in class. So what this approach says, let's sample a fake hash key, which is indistinguishable from the real hash key distribution. And this allows us to focus our correlation interactability task to just one function in this class. Okay. And to answer the question, so formally I require that there exists, so this hash key is sampled according to some distribution. There is some algorithm that samples a key, right?
Yes.
So I require that there exists another algorithm that is given a function f, and it outputs a key, k sub f, that depends on this function, but the distribution of the fake keys is indistinguishable from the real keys.
Okay, so the point is it like in the real protocol, is it the case that I could actually execute the real protocol also with a fake, like it's not a disjoint set, right? So it could be that it's the same, they are over the same domain, or?
Yes, definitely.
Okay, thanks.
Yeah, the hash keys may be a subset of the real hash keys. It's not going to be the case, but for example, so okay, in the real constructions, what we usually do is that this key k is some encryption of 0, and k sub f is some encryption of f. Okay, if it helps you to think about this like that, then maybe actually it may be actually a good way to think about it. So again, k can be simply some encryption of 0, and k sub f can be encryption of f, and semantic security of the encryption implies the indistinguishability between the two distributions. I hope this helps. Any other questions?
So I have a question. So is it important to consider statistically hard to win games, or is it okay to also consider computationally hard to win games?
No, if I replace statistically here with computationally hard to win, we still get the correlation interactable hash. However, some more statistical correlation interactability have some special features. So essentially allows you to get statistical zero knowledge. We don't get that. I can explain later why, but yes, if we replace statistical hard to win here with computational hard to win, we still get the correlation interactability, but just the regular correlation interactability we know.
But then in point 1, is it computationally indistinguishable or statistically indistinguishable?
No, it's computationally indistinguishable.
Okay.
I mean, at some point you have to finish using all your assumptions, right? Like at the end of the day, your proof has to terminate. So you can't. So if you make this a computational property too, then you're gonna have to prove that computational property holds somehow.
Yes, exactly. It just makes both the construction and proof simpler. Any other questions? Cool. Okay. Okay, I see there is another question. Chris?
Oh, I just wanted to mention the statistical correlation and tractability lets you get a proof rather than an argument system.
Right. Sorry.
Yeah, so if that's what you want, then this is a helpful property for that.
Yeah, I confused. Okay, so yeah, it's not statistical knowledge, it's proof. Thanks. We anyway don't get either, so but yes, cool. Okay, so now we know what correlation intractability is. We have some sense how we can approach the problem of constructing it. And I want to talk now about a new strategy for constructing correlation intractability. Okay, so I'm going to take you back to the trivial case of length expanding functions. So again, we have a function that takes a small domain and expands it to a larger range. Good. And I told you about this construction that simply samples a random R, and the hash function is constant, so it doesn't depend on the input X. So for any input X, h of X is simply R. And let's try to kind of take this very trivial construction and put it inside the complicated, somewhat statistical CI paradigm. So the fake hash key here would be just the key. And here we have statistical indistinguishability. And for every f, we can say that the probability that there exists a correlation, that there exists an x such that h of x is equal to f of x, is simply the probability that R is in the image of f of x. And if this image is exponentially sparse compared to the range, then this probability can be negligible. Right? So again, and therefore we get that this construction is correlation intractable. And our idea for constructing correlation intractability for general functions is to kind of impose this picture also when the function f is compressing. So my goal now is to draw something like this also when the function takes a huge domain and compress it to a small range. Perfect. So now our function looks like that. And now we cannot sample a random R and claim that with negligible probability it falls in the image of the function, because the image of the function may possibly cover the entire range. So now our construction will consist of h of x will consist of, or will use a different hash function, which we're going to call h prime. And the hash function h will be simply defined by h prime of x plus r, where r is this random string we sampled like before, and which is a part of the hash key. And h prime of x is a special hash function. So what am I gonna require from h prime? So again, for every function in the class f, I want that there exists a distribution over fake hash keys that is indistinguishable from the real distribution of keys. And I also want that the correlation function between h prime under the fake hash key and f, which I simply define as h prime under kf plus fx modulo 2. So I want that the image of this correlation function is exponentially sparse in the range. Okay, and I'm going to say that in such a case, h prime with the fake hash key and f have a sparse correlation. So again, I moved from looking at the function h to looking at the function h prime plus f. And I'm claiming that if these two properties hold, if I have a distribution of fake hash keys for every function f that is indistinguishable from the real hash key, and if the correlation between h prime under the fake hash key and f is sparse enough, then I'm claiming that we get that h is correlation intractable. And to see this, notice that that the probability that there exists an x such that h of x is equal to f of x, namely the probability that there exists a correlation, is equal to the probability that h prime of x plus f of x is equal to r. I just switched the sides here. And this means that the probability that there exists a correlation is equal to the probability that R is inside the image of this sparse correlation function.
Ahmed, there are a couple of questions. People are
Okay.
asking, so you're doing mod 2 operations here. So is the string R and H prime K of X, is that a multi-bit string, or are you just computing over, I mean, is it like a vectors, you're doing mod 2 over vectors, or you're doing over the entire integer space?
Yes, so these are two binary vectors, and I'm just doing bitwise addition over Z2. Okay, this is just XOR if it's easier to think about it that way. Okay, again, this is a vector, this is another vector, both are binary vectors. I'm just XORing both bit by bit.
Yeah, thank you.
Okay. And this choice is arbitrary. Again, you can do these arithmetics and these arguments over the integers. Two participants raised hands. Okay, I can take questions.
So is another way to see this merely that you want H prime of X to be close to F of X? Did I read that correctly?
Notice that this is not necessarily around 0. Okay, and in fact, so from the one hand, we want that kf is indistinguishable from k, and one way to say this is to say that kf hides f in some sense.
Yes.
So intuitively, at least, k sub f cannot be close to f, because then it may reveal something about f. So this image is not necessarily centered at 0, but we require that there are very few possible values for these two for this sum.
Okay, so H prime not necessarily close to F, but it's close to some shift of F then.
Some shift, or it won't be a shift. This shift you're talking about has to be somehow cryptographically hidden. So it's not that simple. But so again, this image it's not right. It's not really a Hamming cycle inside inside the range. It's simply it's simply a way to say that the image is sparse.
Okay, thanks.
Okay. Any other questions? Cool. Okay, and now I think I convinced you that if these two hold, then we get that H is somewhere statistical correlation intractable. So again, I reduced my goal from constructing correlation intractability to getting this kind of sparse correlation between H prime and F. Yes, I see there's another question. Okay. So again, our goal now is to construct sparse correlations rather than correlation intractable hash. Perfect. And now I'm going to show you how to do that under standard assumptions. Good. And I'm going to start with a very modest goal of constructing sparse correlations for linear functions. I'm going to take linear functions over Z2. Okay, so a linear function is simply defined by a matrix. Again, we're interested in compressing functions, so it's going to be a fat matrix. So it's going to take inputs of length n and map them to input of length m. And the picture looks like that. Good. And the construction I'm going to show you is under DDH, and then I'm going to say that it can be generalized to be constructed under other standard assumptions. But let's for now focus on the DDH construction. So in DDH, we work in a setting where there's a multiplicative prime order group G, and there's a public generator small g in this group. And I'm going to use additive notation. So whenever you see that I'm adding two group elements, then what I actually mean is that I'm multiplying these two. When I'm multiplying an integer with a group element, then I mean to take this element to the power of z, the integer I'm multiplying with. And I'm going to be really crazy about a different notation. I'm going to even add the group elements with integers. And what I mean by G1 plus Z in this case is G1 times G to the Z. I'll try to make this as little confusing as possible. And this notation in particular allows me to multiply a matrix of group elements. So now I have a matrix of group elements of length m over n, to multiply it by a vector of integers, or in particular, a binary vector. So when I multiply this matrix with this binary vector, I'm gonna get a vector of group elements, again, according to this notation. Any questions regarding this? Good. Okay, so why can be DDH useful for constructing sparse correlations? So one implication of the DDH assumption is that rank 1 matrices are indistinguishable from general random matrices. More specifically, if I take a random matrix of group elements where the exponents form a rank 1 matrix, so the vectors here in the exponent are just multiples of, are scalar multiples of some random vector R, then the DDH assumption tells us that this random rank 1 matrix is indistinguishable from a matrix that I sample totally at random. Okay, this is pretty standard. So again, I know that random rank 1 matrices of the group elements are indistinguishable from totally random matrices of group elements. And why our rank 1 matrices are useful or interesting in our case? Notice that rank 1 matrices have a sparse image. Okay, this is high school algebra. If you take a rank 1 matrix and multiply it by an integer vector, then you will get that the image of Rx is sparse in the domain G to the M in this case. And the idea, like you can guess, is to construct a hash function where the correlation function that we get between H with a fake hash key and F is a rank 1 function. Any questions? So this is a high level idea. Now I'm going to show you how to actually implement it. Okay. So based on this idea, I'm going to define, or at least as a first attempt, I'm going to define my hash function as follows. So my hash key is just a random matrix of group elements of size m over n, and I'm going to denote it by k. And we take an input to the hash, and we simply multiply it by k to get a vector of group elements. This is my hash function. It's pretty simple. Okay, this is the, I love pictures, so this is the picture for this hash function. So now let's try and define the fake hash key for a function f in the class to be the sum of a random rank 1 matrix and the function, the matrix defined by the function f. Okay, so again, I have a distribution of real hash keys, which simply samples a random matrix of group elements, and now I'm defining the fake distribution for a function f in the class. And this is
I'm confused about something very, very basic, which is where's the multiplication? Where's the matrix multiplication happening? Like matrix multiplication requires addition and multiplication, right? And
right.
G is a group, so
right. So okay, so so notice that this vector is in the plane, right? And this matrix is in the exponent. But you can always, so this vector consists of zeros and 1, and basically, so let's say I'm multiplying the first row here with the column here. So wherever I have a 1, I will add the corresponding group element to the multiplication.
I see. So it's all happening in exponent. I see. Okay.
Yes, it's happening in the exponent, but because one of the sides is in the plane, you can still perform. Right? All you're doing here is multiplying bits with group elements. This is doable. And then lastly, you just add whatever you left with.
Right.
Add
Okay.
in the group, meaning multiplying group elements.
Yes.
Good. So again, okay, so I told you how to sample a real hash key, and now I'm telling you how to sample a fake hash key for some function in the class f. And in order to sample a fake hash key for f, I'm sampling a random rank 1 matrix R, and I'm adding the matrix defined by the function f. And what this essentially means is the following. So I'm taking a random rank 1 matrix, and I'm adding the matrix of group elements that has the entries of the function in the exponent. So if f1 to fm are the rows in the matrix defined by f, then this matrix I'm looking at is g to the f1, g to the f2, etc. This 2 here is by mistake, so just ignore it. And again, adding these two matrices, meaning getting this matrix on the left. So every row here is some scalar multiplication of a random row R plus the row defined by the function. Any questions? Okay. And remember, the first thing I required from fake hash keys, that they are indistinguishable from real keys, real hash keys. And we know that under DDH, this matrix is indistinguishable from a random matrix, and therefore also this matrix plus F is indistinguishable from random. Is there a question?
Yeah, I have a question. Can you repeat what is this matrix for f again? So f was a function from some domain to a single bit, right?
No, so f is this linear function that is defined by a matrix, right? So let's go back. So again, my target class now is a linear function. So I want to construct correlation intractability for linear functions. And linear functions, how are they defined? Generally by a matrix, right? M over n. They take a vector of length n and compress it to a vector of length m. So this is a binary matrix, and I right, just matrix of zeros and one. And what I'm saying is that in the hash key, I want to embed the description of the function, but I do it in the exponent. Okay, because I'm working with group elements here. So my fake hash key is going to be this random rank 1 matrix, and I'm going to add in the exponent the entries of f. Okay.
But isn't your function defined over Z2? But here it's
right. So okay. So again, the function itself is defined over Z2, but this matrix, it doesn't contain zeros and one, but rather it contains group elements. And more specifically, whenever I have a one in the function description, I'm going to have a G here, right? The generator. G to the one is G. Wherever I have a zero, I'm going to have a one, which is an element of the group because it's just G to the zero. So this becomes a matrix of group elements. And what essentially I'm doing here is taking a rank 1 a matrix of group elements and adding to it the description of the function over the prime ordered group, and I'm going to end up with a matrix of this form.
But doing this over Z2 wouldn't be same as doing it in the exponent of this group, right?
Say again.
So if you are actually computing this function over Z2, and here you're computing this over the exponent of this group, but those things won't be the same because you can add two ones and you get a 2 here, but you get a 0 there.
Definitely. So you're already seeing one problem in this construction, and that's why it's called attempt 1. Notice that, so what Akshay is saying is that now, if I would like to multiply this matrix of group elements by some vector x, then the multiplications are going to be, the arithmetic is going to be modulo p, the order of the group, rather than modulo 2, and that is correct actually. Any other questions? So again, think about matrix, a rank matrix, And I also multiply by G the entries that correspond to 1 in the description of F. Is that clear now? Okay, if there are any questions, please ask. We have plenty of time. Cool. Okay, and like I said, under the DDH assumption, this distribution of fake hash keys looks indistinguishable from a random distribution of real keys, and that's because this random rank 1 is indistinguishable from a random matrix, and addition with F doesn't change anything. So we at least, yeah.
Sorry for a stupid question, but why couldn't you use KF as your hash key then? As your hash
Okay.
key?
So notice that my goal is to construct correlation intractability for an entire class. When I define the correlation intractable hash, I'm not sure which function the adversary may choose to attack. So my goal, and this is essential, is to construct correlation intractability against the entire class. We saw before that constructing correlation intractability for a single function is actually easy. So we're not interested in this case. We're interested to construct correlation intractability against an entire class. And one way to do it is to define a fake hash key for every function and then claim correlation intractability under the fake hash key for every function. I hope this answers your question. Okay, so again, we have that we're constructing correlation intractability against the class of linear functions, and this fake key, it appears only in the proof of correlation intractability. It doesn't appear in the real construction. The real construction simply samples a random hash key K.
So Tamer, a question. This is Vinod. The trivial construction would be, for a single function would be compute the function and add 1 or something like that, right?
Yeah.
But then the description of the hash key depends, it reveals F, reveals the function.
Right.
Now, if you say that, you know what, I don't want, a correlation intractable for a class of functions. I just want it for a single function, but the key has to hide F. Is that also trivial, or is it trivial? If it's not trivial, is it useful?
What does it mean to hide F if there's only one F?
Good question. In the applications, for example, right? Once you fix a protocol, don't you actually know what the function is and the commitment scheme and so on? The public key for the commitment scheme, isn't the F fixed?
So once you fix, I'm going ahead, but the function will contain the secret key underlying the commitment.
That's right. That's what I meant by hide, which you cannot reveal.
Right, but you want that. Okay, so notice that. What I'm missing here.
So I guess this is what you're doing is one way to formalize, this requirement, that looking at the key, you can't tell what the function is. I'm just wondering if there is a way to sort of do it without going through the statistical computational,
I see what you mean. So you're saying I have a, you're saying, okay, we have constructible hash for some function that hides, so the hash key hides F. I think it would work for NIZK, but if you can sample a hash key for every F and still hide F, then you can sample hash key for a dummy function, right, and get correlation intractability for a class.
So one way. So so Chris was asking, what does it mean to hide F, right? So here is one way to do it. One way to think about it. If I give you the hash key, right? It should be, it's a very sort of tailored definition, but it should be hard to do something. For example, sort of break the hiding of a commitment scheme. So that's one way to sort of formalize what it means to hide F, right? That should be sufficient for NIZKs. That's what you're saying, right?
Yes, but I'm saying maybe if you can do that, then you already have a construction of correlation intractability for an entire class. Simply sample a hash key for a dummy function, the zero function. I don't know.
Okay, thanks.
Cool, thanks for the questions. Okay, So now I showed you that for every function there exists a distribution over fake hash keys that is indistinguishable from the real distribution of hash keys. And now it remains to show you that this fake hash key defines a sparse correlation with the function itself. And this essentially will imply correlation intractability, like we've seen. So how does the hash function look under the fake hash key? So multiplying the fake key with an input x is simply consists of two parts. So the first part is r multiplied by x plus f of x. And this plus again is over the group. And if we switch sides, then you can see that, again, this is very high level, but the hash function with the fake hash key on x minus, and this minus again is over the group, f of x in the exponent is equal to some rank 1 computation, rank 1 matrix multiplied by x. So if this is our kind of correlation function, and notice that it does define some correlation between the fake hash and f, then this function has a sparse image, right? A sparse correlation. So it seems that we are very close to achieving our goal, and the only problem, and I think people already noticed it, is that this correlation is over G, and it considers the computation of f over the exponent. So first of all, the computation is not in the plane, and second, the computation is not modulo 2, but rather modulo p. So we're getting there. This is not quite what we need. Any questions? Good. So the idea is to translate all these computations that are performed over the group G to computation over Z2. Okay. As a second attempt to construct our hash function, I'm going to assume we have this magic tool that I'm going to call parity encoding over G that takes a group element G to the Z and outputs the parity of its exponent Z modulo 2. I see we have a question.
Yes. So previously you mentioned you want to compute the image from the group element to Z2. What's the purpose of that?
Okay. So again, our main goal is to get a correlation function between the hash with the fake key and f that has a sparse image. And like I showed here, we have some kind of a correlation function between h under the fake key and f, but this correlation function, it considers the correlation between the hash and the function when it's computed in the exponent. Notice that this matrix is a matrix of group elements, right? If we go back, then the function here is described, the description of the function is embedded into the exponent. Mm-hmm. So the correlation I'm getting here is between the hash with the fake key and the function in the exponent. And you may see, well, maybe this is just some syntactical issue. That's not really a problem. But then, so this function, it relates to our Sigma protocol, and it basically defines the bad challenge function. And right, so it's not really clear how to take such a sparse correlation and use it to claim correlation intractability in a Sigma protocol where all the computations are done in the plane. So you would require some form, something that will take this value and translate it into and convert it into f of x. And it's not really clear how to do that.
So in other words, there might be a way that if the f function is defined alternatively, say the image is also a group element, then we can maybe stop there.
Yes, but again, this is not only a syntactical issue. It's not only working over G versus working over Z2. Working over G by itself introduces this, introduces the cryptographic hiding we're getting from BDH. So this is saying that you cannot actually see f of x, And maybe it's inherent that you need that the computation of the computation of the bad challenge is actually in the plane. It can be seen by the verifier. I don't know, but I don't think it's purely a syntactical issue.
Okay.
Cool. So again, our goal is to take to somehow translate all these arithmetics to computations over Z2. And I'm going to assume a magic function, which I'm going to call parity encoding over my group G, that takes any group element, G to the Z, and outputs the parity of the integer Z in the exponent. Okay. And I'm sure many of you already think that this is impossible assuming DDH, because if this can be computed efficiently, then we essentially break the DDH assumption, and this is true. But for now, let's assume we have such a function that takes G to the Z and outputs the least significant bit of Z. And now my hash function will be defined exactly as before. But now I'm going to take this vector of group elements and compute its parity. So now, rather than outputting G to the Y, which is essentially the product of K multiplied by X, I'm going to output Y modulo 2. And now again, I'm going to sample the fake hash key as before, and we already saw that K sub F multiplied by X consists of Rx, which is a rank 1 matrix multiplied by X, plus f of X in the exponent. But now I apply parity to this vector, and what I will get is the parity of Rx plus f of X. And now this f of X is over Z2 rather than modulo P. And now what I get is that the correlation between the hash with the fake key on X and Fx is equal to the parity of Rx. And because Rx has a sparse image, so does the parity of Rx. Good. So now I got what I needed. I needed that the correlation between the real F in the plane and the hash with the fake key is sparse. And this is true in this case. Julio. Question?
So yeah, you don't want F to wrap up mod P, right? So you want the coefficients of F to be small. Is that correct?
Yes, yes. So the coefficients of F are binary.
Binary. Okay.
Right? And yeah, and the dimensions are M and N. So
okay, fantastic. Yeah. So thank you.
Any other questions?
Tamer, maybe you said this, I missed it. What do you mean by parity here? Do you mean computing the hardcore bit of G, or what?
No, so I'm assuming, so this encoding doesn't exist. At least you cannot compute it efficiently if you don't want to break the edge. But parity here is just taking a group element. So the parity is defined according to the generator G. So essentially, you take a group element and you output the parity of its discrete log. That's what essentially parity does. Okay. So parity is just the parity of the discrete log of a group element.
Okay. Thank you.
And again, if this parity, if I can compute parity efficiently, then my hash function that I define as before plus this parity encoding, it defines a sparse correlation between the hash with a fake key and F for every F. Any more questions? Perfect. So like I already mentioned a couple of times, if I can compute this parity encoding efficiently, then I essentially break the DDH assumption. So we're gonna have to find a better way to compute this encoding. And we're going to use an idea that was first used by Boyle, Vilboa, and Ishai in a way different context. So what they essentially do, they suggest a way to compute what they call a distributed discrete log group elements, and we use essentially the same ideas to compute a different parity encoding. So now we do not require that the parity encoding outputs the parity of the discrete log, but rather we require a much simpler and weaker property. The only thing we require from the parity encoding is that it preserves the difference between the parities of different group elements. So we require that if we take a group element H, then the parity of H and the parity of H multiplied by some g to the y is equal to the parity of y. Okay, and we require that this holds true for bounded values of y. And I'm not going to go into the details, but I think it's not that hard to be convinced that this is the only property that we use in the ideas I just described in the construction. So again, our construction of the correlation intractable hash is simply multiplying this random matrix of group elements by the input, and then applying the parity encoding, which I'm going to describe in a bit. But this parity encoding is no longer this parity encoding. It doesn't output the LSB of the discrete log, but is rather an encoding that preserves the difference between the parities of the discrete logs of two group elements. Any questions? Okay, so I told you that computing the parity of the discrete log is hard because you cannot. Okay, Chris, question?
Yeah, just to make sure I understand. So, are you just using the fact that so you've got this hidden Rx in there, and then you've also got the F times X in there, right?
Mm-hmm.
And we're taking the parity of the sum of these two things.
Mm-hmm.
And so is like the Rx playing the role of H here in some way? Is that how I should think of it?
Yes,
or?
yes.
Yeah, okay. And so we get the parity of F of X, but kind of shifted by this unknown parity of Rx.
Yes, definitely. So Y here is F of X, H is the Rx. Yes.
Okay, and then the polynomially bounded Y has to do with, because F of X is not automatically mod 2, right? But it's a small integer?
Yes, it's smaller than n.
Okay, awesome. Thank you.
Any more questions? Perfect. Okay, so okay, the animations are buggy here in the slide, so I'm gonna show everything. Okay, so I'm going to take you back to the first parity encoding I showed that I claimed is cannot be computed differently. And I told you that it essentially outputs the parity of discrete log. And one way to interpret this computation is as follows. Let's look at the line of group elements that starts with 1, then g squared, and so on. And now I'm saying that in order to compute the parity of some group element h, which is equal to g to the t, just start walking on this line until you reach 1. So walking means just dividing by g over and over again. And you walk over this line until you reach 1. And the number of steps is going to take you until you reach 1 is clearly the discrete log of this h. And now I tell you, once you reach 1, take the parity of the number of steps. So the parity of h is essentially the parity of the number of steps to reach 1 in this interpretation. Okay, so this is another very inefficient way to compute the inefficiently computable parity encoding. Okay, why do I show you this? Because now I'm going to suggest a bit different way to compute a parity encoding in a way that I preserve the property that I was targeting. So now I'm not going to compute the discrete log and take its parity, but rather I'm going to compute the distributed discrete log. And what does it say? So we say the following. Let's define a set of group elements using some PRF. So I'm taking a random pseudo-random function, and I'm defining a set of reference points over this line of group elements to be all group elements that map to 0 under this pseudo-random function. Okay, so this is just an arbitrary random set of group elements over this line of group elements. And now I'm saying, instead of walking on this line until you reach 1, walk until you reach the closest reference point. So in this case, if you start with h and you start walking, meaning dividing by g over and over again, then you're going to reach z2. And let's say this takes you t prime steps. So now the parity of h is going to be defined as the parity of this t prime. So now the parity is no longer the parity of steps it takes you to reach 1, but rather the parity of number of steps it takes you to reach the closest reference point. Okay, so again, this is our new parity encoding. And I claimed that the parity of h times g to the y plus the parity of h is equal to y, and this is all we needed for our sparse correlation. And why is this true? Notice that h and h times g to the y, if y is sufficiently small, they are kind of close to each other. And now the number of, if t prime was the number of steps it took h to reach z2, then the number of steps it will take h times g to the y is t prime plus y. And the parity of this plus the parity of this is exactly the parity of y. This is simple math, simple calculation. Now, this is true, but not always. There's this asterisk here. Notice that when I have a red reference point between h and h times g to the y, then everything here fails. So this is true as long as I don't have any red points between these two green points. Is there any question?
Not a question, Tamer, but just to give you a quick time check, you have about 5 minutes left.
Oh, really? Okay.
We can maybe a little bit, but yeah, just to give you a quick time check.
Cool.
Yeah.
Okay. Okay. I'll try to speed stuff up. Okay, so you've got to believe me that if the number of z's is if we have just the quite right amount of reference points over this line, then we will get that we will get correctness with high probability. We will get that this property holds with high probability. And on the other hand, the algorithm will be efficient because the closest reference point will be indeed close to h. Okay. Are there any questions on that? Okay, so again, to wrap it up, our hash function simply multiplies by a random matrix of group elements and then applies this parity encoding to the vector of group elements, element by element. Okay, so all of these ideas can be abstracted. Yes, Julio?
Are you going to explain how to deal with the error, or just can you give a brief indication?
Okay,
there's going to be a polynomial, inverse polynomial.
Right. So there will be an inverse polynomial error here. If you're still not convinced that this is not a problem by the end of the talk, let me know. Okay. So notice this probability is high, but it's not overwhelming. Okay. It's not 1 minus negligible. It's 1 minus 1 over poly. Thanks.
We can talk about it at the end of the talk.
Sure. I'm sure it will be clear why this is not a problem. So again, all of these ideas can be abstracted using a new primitive, which is called the Trapdoor hash, that was originally used to construct private information retrieval, and it can be constructed under GDH, but also under QR, DCR, and LWE. And we can very easily bootstrap this to support constant degree polynomials and not only linear functions. So now we know that under these standard assumptions, we have correlation intractability for constant degree polynomials, which is already something. But notice, and now I bring back our outline, our goal was to construct NIZKs for NP, and for this we know we have to construct correlation intractability for the bad challenge function, but all we get now under these standard assumptions is correlation intractability for constant degree polynomials. And it doesn't seem that the bad challenge function can be described as a constant degree polynomial in any sigma protocol that we know. So this is not sufficient for NIZK, not yet. So now we ask whether can we get more from this sparse correlations paradigm. So let's go back to the sparse correlation thing, and we observe that. So we claim correlation intractability because we said if we sample a random R, and if our correlation is sparse, then this R is with negligible probability in this sparse image of the correlation function. But we observe that it's not only that R is not in the image with overwhelming probability, but rather R is far from the sparse image with overwhelming probability. So if we take the Hamming ball around R, then with overwhelming probability, it does not intersect with this red image of the sparse correlation. What does this mean practically? This means, so I'm not going to go through the math because we're a bit short on time, but this means that it's not only hard to find correlation between h of x and f of x, an exact correlation, but rather it's hard to find a correlation for any approximation of the function f. So it's hard to find an x such that h of x and f of x are not only equal, but are even close. Okay? And this leads us to define this stronger notion of correlation intractability, which we call CI for approximable relations, or CI-Apx for short, which I'm going to talk about next. So what do we mean by saying that some hash function h is correlation intractability for relation approximable by a function f, or CI-Apx for f? We say that h is such a function when any adversary cannot find an x such that h of x and f of x are close in Hamming distance. Okay, so this requirement it's stronger than correlation intractability, but it allows us to consider simpler classes of functions. And I want to say that this notion it's not a new notion of correlation intractability. It's just correlation intractability for approximable relations and rather than searchable relations. So these are relations that do not only contain x and f of x, but rather contain x and the Hamming ball around f of x. Okay, and we say that a hash function is CI-Apx for a function class if it's CI-Apx for every function in the class. And from what I explained in high level, it holds that if we can instantiate this sparse correlation paradigm, then we get CI-Apx for a function class f. So what does this mean? So it means that under the standard assumptions DDH or QR, DCR, or LWE, essentially any standard assumption that gives you trapdoor hash, you can get a CI-Apx for constant degree polynomials. So now we don't get correlation intractability for constant degree polynomials, but rather we get correlation intractability for approximable relations by constant degree polynomials. Okay, and this is way stronger as it appears than just correlation intractability for constant degree polynomials. But now it's not clear how powerful this notion is unless we quantify it using searchable relations, because that's essentially what we're looking for. So and to do this, to understand the power of correlation intractability approx, let's consider this standard notion of approximation. So I'm going to say that a function class f has a probabilistic representation by a much simpler class C. If for every function in this f, I can sample a random function C such that for any x with overwhelming probability, I'm going f of x is going to be very close to C of x. Okay, so again, I have an f, a function, and I'm asking that for every x, the distribution, some distribution over functions in C gives you that C of x and f of x are close with overwhelming probability. Okay, this is a very standard notions. And one of the more important theorems in this work is that if F has a probabilistic representation by C, then CI-Apx for C immediately implies correlation intractability for the class F. And again, we hope that this class C is much simpler than this class F. And this means that in order to construct correlation intractability for a powerful and expressive class F, all we need is to construct CI-Apx for a much simpler class of functions C. And this immediately implies that under many standard assumptions, we have correlation intractability for all functions that have probabilistic constant degree representation. And to give you some sense about the power of this statement, I just want to say, and this is pretty standard, that CNF formulas have probabilistic constant degree representation. So we already get correlation intractability for CNF formulas under standard assumptions other than LWE. The proof is not that hard, so I'm going to skip it. Yes, any questions? Okay. So the proof of this theorem is really simple and intuitive. So again, our outline now looks like that. So we started with Trapdoor hash, and we were able to construct CI-Apx for constant degree functions. And this, what this theorem tells us is that this gives us correlation intractable hash for functions that can be probabilistically represented by constant degree polynomials. And now the only thing we have left to do is to show that bad challenge has probabilistic representation as constant degree polynomials. And why are we hopeful that such a probabilistic representation exists? Because we know that this class of functions already captures KCNF. And maybe bad challenge can be described using a KCNF formulas and maybe some other stuff. Any questions? Cool. So what I'm going to show you real quick next is that under the LPN assumption, we have a sigma protocol where the bad challenge function has a probabilistic constant degree representation. And if we do that, we finish.
Yes.
So again, just to go back a bit. So my goal now is to show you that under the LPN assumption, there exists a sigma protocol where the bad challenge function has a probabilistic constant degree representation. And all I'm going to say in this regard is if we take the commit then open sigma protocol that we've seen before, where the bad challenge function is simply some polytime verification algorithm applied over the extracted values that we extract from the first message, then okay, and now we observe that, or we use the fact that CNF satisfiability is complete for polynomial time verification. Okay, this is a simple. This is simply the some very special case of the Cook-Levin theorem. And okay, I'm not going to go through the details, but we can adjust the protocol a bit. Any commit and open sigma protocol, we can take it and adjust it a bit using the Cook-Levin idea of appending a witness to of turning essentially any polynomial time verification to a verification of the satisfiability of some KCNF formula by appending a Cook-Levin witness. So we do that, and we get a protocol where the bad challenge function is now not an arbitrary polynomial time computation over the extracted value, but is rather simply a 3CNF formula over the extracted values. Okay, so now our bad challenge function consists of first extracting the values underlying the commitments and then applying a 3CNF formula. And now, okay, so using standard randomization techniques, you can show that the 3CNF formulas can be probabilistically represented by constant degree polynomials. And further, we show that under the LPN assumption, there exists a commitment scheme which is extractable, and where the extraction function can be probabilistically represented by linear functions. So these are, of course, polynomials of degree 1. So combining these two facts, we can imply that this bad challenge function has a probabilistic representation by constant degree polynomials. Okay, and now we can complete the picture and say that under LPN there exists a sigma protocol where the bad challenge function has probabilistic constant degree polynomial, and therefore we can use our construction of correlation intractable hash, which has security under, in particular, DDH. Okay, so there are many open questions, of course, that one can ask here. In particular, one can ask whether there are other applications of this new correlation intractability for approximable relations framework. Maybe applications to ZAPs or to some complexity theory results. Another question maybe is whether we can minimize the set of assumptions on which we base the security of our protocol, and also whether we can get statistical zero knowledge maybe, or NIZK proofs rather than just arguments, which are protocols with the computational soundness. That's it. Thanks. I'm happy to take any questions.
I have a question. So if you is the bootstrapping from correlation intractability for linear relation to constant relation generic or specific?
Yes. So I can just explain it in one sentence. You simply take so a constant degree function is simply a linear function over the tensor of your input, right? Over some constant degree tensor of your input. So instead of applying the hash function on your input, you apply it over the tensor of your input, the tensor product of your input.
So that's the, so and also the bootstrapping of the approximation also happens here.
So the approximation doesn't affect the correctness of what I said. The bootstrapping can be even done in the trapdoor hash level. So it can be either done in the trapdoor hash level or in the correlation probability level. It doesn't matter. It's the same construction and same result.
Okay, cool. Thanks.
I have a question. So does this probabilistic representation satisfy this composability property that if you have probabilistic constant degree representation of f and g, and f composed with g also has this probabilistic constant degree representation?
Yes, but one has to be careful. There are many technicalities here that I kind of I didn't even mention. But in general, yes, probabilistic representation is composable, but we're dealing here with also with extraction of commitments, which can be also invalid. So there are lots of technicalities that one has to be careful with here. I hope I answered your question.
So if there are no other questions, thanks, Tamer, for the talk.
Thank
you. Yeah, we'll be having the second seminar on Tuesday. So thanks everybody for joining in today. Thanks, Tamer.
Thanks.
Thanks so much.
Thank you.
No, so we'll just stop the recording right now.
Huh?
We'll just stop the recording right now, right?